So if I attach from here to here with the curve, I can see kind of a slice of this thing. Do y'all see how that plane cuts that cylinder? And if I connect these together, it's like a slice of bundt cake. Have you ever had a bundt cake? Kind of like a slice of bundt cake. Not quite, but close enough. Right? That's our region E. I draw its shadow or projection onto the ground. I draw that in two-dimensional space over here. X, Y, it goes through 0. It hits up here at 3. And then over 1, up 3, hits this point. So this right here is that piece on the ground, right? That on the ground looks like a type 1 region to me. I like that as a type 1 because if I draw a vertical segment in there, the top and bottom are always the same curves. My x's are bound between two constants, so I should be able to set up my restrictions on x and y right now. X restrictions are 0 to 1. Y restrictions, so you have to know the equation of this line, which is y is 3x. And then the equation of this line, which is y is 3. It's constant. So this is going to go from 3x to 3. And the last thing now is my restrictions on z. So the bottom of this solid is 0, isn't it? And the top is this part of the cylinder, isn't it? So the cylinder equation is here. You have to take that and do what? Solve for z. You're going to get a plus or minus square root when you do that, but you're only looking at the plus because it's the top. So solve that, you get z is equal to square root 9 minus y squared, right? So this is square root 9 minus y squared. Bless you. And then you set it all up, right? So you'll have triple integral 0, 1, 3x 3, 0, bless you, square root 9 minus y squared. We are integrating z, d, z, d, y, dx, because it's type 1. And then you go do it. All right. I was just thinking about this. Are there quadruple integrals? No? Sure. Not in this class, but I mean, could there be? Yeah. And if you did it, you could say, okay, well, imagine that we have this, our region, I'll call it, I don't know, E, F, okay? It's a quadruple integral over F of some function of not 3 variables, but 4 variables. I'll say t. D d, yeah, I mean, like dv was d volume because the E had a volume, right? But what is one dimension higher than volume? You know what I'm saying? Like we don't have a nice thing for it. So I could call pretty much anything I want. dh, because we could call it a hypersolid. Sometimes a solid that's one dimension higher than 3 is called a hypersolid. I could do that. And what you would have to come up with is restrictions on x, y, z, and t, right? X would be between two constants, let's say a and b. Y would be between two functions of x. Z would be between two functions of x and y, and t would be between two functions of x, y, z, x, y, z. So you can generalize this, but we start to lose we start to lose application because we really only need 3D, 4 really, to work with a lot of things in the real world, 3 or 4 dimensions. So, all right. This is what I was saying. There's different types of triple integrals on, casting shadows on different planes. Now we move on. So if you recall that from double integrals, if you're taking the double integral over d of 1 dA, that this represented the area of d. Remember I said that? If you take a double integral of the constant 1 function over some region d, this answer is the area of the d. Well, it works exactly the same with triple integrals. If you take the triple integral over e of the constant 1 function dv, you get the volume of e. Didn't we just do that problem? Oh, no, we didn't. Sorry, we did not do that problem. That problem is the exact same region, right? That's the exact same e that we just had. But there's not a function that we're integrating, right? It's saying find the volume of that, right? Find the volume. So all I'm going to do is set up the same triple, 0 to 1, 3x to 3, 0 to square root 9 minus y squared of 1 dz, dy, dx. If you integrate that, then you will get the volume of that solid. See the difference? Okay. It turned out to be 3. I just had the computer do it. Now, I think that's where the notes end, right? Is that where they end? I spent some more time today. There's a little more in this section. I have not updated these notes online, but there's some stuff at the end of this section I think is worth looking at. And we won't do an example, but we'll talk about it, all right? That doesn't mean you won't have it for homework. You will have it for homework, but I'm not going to work through one. Application of a triple integral. We saw when we had a lamina last class, if that lamina had a density function, we could find its center of mass. We could find its moments of inertia, things like that. Well, we don't like laminas because we live in 3-dimensional space. So, I mean, I'd be more interested in finding the center of mass of some object, right? This is 3-dimensional. So if I have an object in 3-dimensional space, and I know its density function, then we have the following results. The mass is the triple integral of the density function. Wasn't that exactly what it was with the lamina? The mass was the double integral of the density function. So the mass of a 3-dimensional object is the triple integral of the density function. Then we had, with last class, moment functions. But because we were only working with 2 variables, we had the moment about x, the moment about y. Here, because we have 3 variables, we have what's called the moment about the xz plane, the yz plane. Here's what it is. The moment about the xz plane, here's what it is. And the moment about the xy plane, which is this. So the moment about the yz plane is the same as the mass, with the exception that you have to multiply by x. Moment about the yz plane is the same as the mass, except multiplied by y. Moment about the xy plane is the same thing, except z. Once you compute all of these, then you can find the center of mass. The center of mass is an ordered triple. It's your x, y, and z coordinates. The x coordinate is your moment about the yz plane over the mass. The y coordinate is the moment about the xz plane over the mass. The z-coordinate is the moment about the xy plane over the mass. So there's a lot of integration that has to take place for you to find it, right? But it can be done. Then you have the moments of inertia, which is the object's resistance to motion, to being rotated about something. So if you want to know the moment of inertia about the x-axis, so you have this object, you're trying to rotate it around the x-axis, its resistance to that motion is going to be measured by this triple integral. So do you see that density function again? But you multiply by y squared plus x squared. And then the moment about the y-axis is this, and the moment about the z-axis is this. So you might imagine those could get pretty messy, but they're doable. I have the homework assignment. Yay. I haven't done these on video yet. I plan on doing those, starting those tomorrow. What's your question? What?
It's like on the take-home, where we have to find the moments of inertia, on the last one, you said which one is easiest, about the x-axis or about the y? So how do we know? Is it like is it the shortest moment of inertia, or? You gotta self-report that.
Someone asked me that question last time.
Did they?
Yeah, right?
And
And I said,
think it.
Think look it up.
I remember that.
Be resourceful. I'm sure you can find it out.
No, I just remember that,
Yeah.
that example.
What you could also do if you wanted to try and, I don't know, see what you can do.
No, I got you.
Okay. All right, that's the homework for that section. Got it? We got 20 minutes left. We have enough time to get into the next section. 12:06. Let me save this. So that's it for 12:06. Just do those problems. All right? Triple integrals and cylindrical coordinates. So just like we did with double integrals, we had type 1, type 2 regions. Then we realized, hey, there's some regions that are not very good, as far as they don't look like type 1 or type 2. So we came up with polar coordinates. So now we have this thing with triple integrals called cylindrical coordinates. And here's how it works. It'll look familiar. Actually, it's going to look very familiar. This is just a three-dimensional version of polar coordinates. We use the same exact conversion. X is r cosine theta, y is r sine theta. This is still a relationship. X squared plus y squared equals r squared. Theta equals arctan of z over x, or y over x, is still valid. The only change with cylindrical and polar is that we have a z to deal with now, right? And all we do is let z be z. So we actually don't change z at all. So let me show you. This is what cylindrical coordinates looks like. If I let my theta be between two constants, alpha and beta is what we used, and I let my r be between two constants, I think we used a and b. Oh, that's not a and b. We saw last class that this would draw this polar rectangle. Remember that from last class? That's what this draws. All we're doing now is turning that, and that's the ground, and we're letting z just be z, whatever it wants to be. So I can imagine going around this space. It's still three-dimensional space, but to get around, someone has to give me an angle to turn. Somebody has to give me a distance to walk out, right? And then just a z value, just how high up to go or how low to go, right? So 3 pieces of information I need to get to a point in this space. r, theta, and z. Do you see how it's just polar with z? Just an up and down now? I remember the first time I was introduced to this, my professor, he was pretty cool. He called this, because we think about Earth, we think about we live in three-dimensional space, right? The planet we live on is a sphere, right? And we'll have spherical coordinates coming up soon. It would be a planet that would look like a cylinder. He called it Planet Schlitz. Because I guess the Schlitz beer cans or something. I don't know. I just never forget that. Planet Schlitz. Cylindrical coordinates is a beer can. All right? That's what it is. You move around, rotate an angle, move in and out radius, and you go up and down. If you do that, you're going to be somewhere on a beer can. So how does this help us in terms of doing triple integrals? Well, nothing changes in terms of the double integral. So if you think of a triple integral as a double integral with one additional integral inside, then the outer two integrals don't change. You still have theta as the outer integral. The next one in is going to be r. And then the inner integral is now going to be your surface top and bottom. That's the big change. Z has to be stuck between two surfaces. So last time we were writing u1 of xy, u2 of xy, right? Previous section. But because we're going to cylindrical coordinates, we have to make a polar conversion. Our x becomes r cosine theta, our y becomes r sine theta. Same over here. So here's an example of a region E. Okay, this is what a region E would look like in cylindrical coordinates. See how the shadow of it is a polar region? That's basically what tells you you need to be in cylindrical coordinates. If the shadow on the ground isn't type 1 or type 2, and it looks more like polar, then you should convert to Cartesian coordinates, which is what you were suggesting you could have done there. Yeah. On the problem that I walked out and let y'all work on, you could have done polar, but you would have had to project it up against the back wall. Okay.
But it was possible, though, right?
It was possible, yes. Now look at how this triple integral is set up. Alpha to beta is your restriction on theta. H1 theta, H2 theta is your restriction on R. U1 of all this junk, U2 of all this junk, that's your restriction on Z. And do you see the all-important thing in here? R. And that's because anytime you're in polar coordinates, you must have this R here. And Cartesian is polar, just three-dimensional. So do not forget the R in the integral when you go to cylindrical coordinates. We should have time for this one. Find the triple integral over the region E of x dv if E is the region bounded by all this junk. Okay, I get to draw this. Okay, what is Z is 0? XY plane, it's the ground. I might need all the ground. Let's see. It's the ground, okay? Just remember the ground is there, right? I'm not going to draw it. Z equals x plus y plus 5. What is that? It's surface. What kind of surface? It's a plane, right? That's a plane. If x and y are 0, where am I? Z is 5. If x and z are 0, what's y? -5, which would put me over here. And if y and z are 0, x is -5, which would put me back here. So if I connect these together, I have this plane, right? It extends in all directions. I have a cylinder, x squared plus y squared equals 4. That cylinder goes up and down, has a radius of 2, which would be, I don't know, 2, 2. I imagine this cylinder going up and down here. This is going to become messy. I'm sorry?
Are there going to be two cylinders?
Yes, there's another one right here. And that cylinder is radius of 3, which is outside of that one. Just a little bit, right? Goes up. They go forever, right? But what the hell does this thing look like? It's the region bounded by all of those. So what about, forget the plane for a second. If it was the region between the two cylinders, it'd be like, I don't know, what does that look like to you? Piece of PVC, toilet paper, paper towel roll, whatever, right? That's what it would look like. But you've come through with the plane, and that plane is going to slice through this thing, isn't it? So it's actually going to come through at some angle and cut through this. And when it does it, it's going to look more like this now, right? And the bottom of it is actually the XY plane. So it's just flat on the bottom, yeah? That's the region of integration. It might, so that's hard for me to draw. Do you see? I mean, I'm struggling drawing that. Because it's hard to draw a plane with a slant on a flat sheet of paper. It's hard to draw that. But if I just think through it a little bit, I kind of get an idea of what it looks like, yeah? Now, let's talk about the projection of that solid onto the XY plane. So we can look at the two-dimensional restriction. The two-dimensional restriction of this onto the ground is going to be that thing that looks like a washer, right? And it's everything in here. And when I look at that, I say type 1, type 2, or polar. Polar for sure, which means I need to do this as a triple integral in Cartesian coordinates. So what's my restriction on theta for that region? 0 to pi. What's my restriction on r then? 2 to 3, right? I'm going to go just the points between 2 and 3, radius 2 and 3. And then the last thing I need to get a restriction on is z. I'm going to put z here. What's the restriction on z? 0 to, so the bottom of this is the ground right here. The top of it is the plane. Solve for z, right? So solve this for z and you get x plus y plus 5. Do you agree? Well, it's already solved for z, so I don't have to worry about solving for z, but that's this. Y'all with me on that? We have a little bit of a problem. The issue is that we went to Cartesian. And when you go to Cartesian, it's the same we went to cylindrical. And when you go to cylindrical, it's the same as going to polar, which means that everything has to, all your x's and y's have to be converted. So this restriction right here should not actually say x plus y plus 5. It should be z greater than or equal to 0, less than or equal to r cosine theta plus r sine theta plus 5. Okay? Understand that? That's everything I need to set up the triple integral. So my integral will go triple, right? You want to go 0 to pi, 2 to 3, 0 to all that nasty stuff, r cosine theta plus r sine theta plus 5. What am I integrating? X. But what's x? I have to convert. r cosine theta. That's it. And then r, because I went to polar, right? I went to cylindrical, which is the same as going to polar. You must have the r in there. And now what are your things out here? dz, dr, d theta. I'd like to do just the first integral, just the first integration. I won't do all of them. Are there any questions, though, on how I did this? Or what I've done? Or why we're here? No? Did it get warm in here? It seems like it got really warm in here.
I think it's just the pressure.
The pressure. Okay, what is the antiderivative of this with respect to z? R squared cosine theta z. R squared cosine theta z, evaluated from z equals 0 to z equals r cosine theta plus r sine theta plus 5 dr d theta. So I now have the pleasure of replacing z with this and this subtracting. The z0 is nice, kills stuff off. The z is r cosine theta plus r sine, that's not so nice. 0 to pi, 2 to 3. Let's see. When I do this to this, r squared cosine theta distributes to each of these. So I get r cubed cosine squared theta plus r cubed again, sine cosine theta sine theta. Am I doing this right? Last one, 5r squared cosine theta. That's it. dr d theta. Now I get to integrate with respect to r. I think I don't have enough time to move on and do more, so let me just finish this off. If I integrate this with respect to r now, I'm going to be in the middle integral now. Antiderivative of this with respect to r is pretty easy to get. So 1/4 r to the 4th cosine squared theta plus 1/4 r to the 4th cosine theta sine theta, and then plus 5/3 r to the 3rd cosine theta. Evaluated 2 to 3. Shit, that sucks. D theta. That does suck. Because I got to replace all my r's with 3 and then with 2 and subtract. I wish it was like 1 and 0. Wouldn't that be nice? But it's 0 and 1. It's not, though. All right, so I think maybe I'll stop there. I don't feel like doing that. But you understand what you would have to do? When I do that, I'm going to have just constants in front of these, right? And you'll have to integrate with respect to theta. How are you going to integrate cosine squared? Power reducing formula. How are you going to integrate cosine theta sine theta? You could do sine 2 theta or basic u sub. That's not worth talking about. Right? That's how that would go? Okay. Let me see what's next. Oh, this is the picture of it. This is actually the rendering of that. You can see the solid in there. You see it in there? We found the volume. No, sorry, we're not finding the volume of that. That's just E. All right. And if you do all of it, it comes out to 65 pi over 4. This is almost the same problem, but it's a volume problem. So you're trying to find the volume of the solid between two cylinders and inside of a sphere. So in between these two cylinders and inside this sphere, you're trying to find the volume. You can do that with a triple integral, can't you? You just have to integrate the one function. How would you do that? Can you tell me what the region on the ground would look like? Almost the same exact thing, right? 2 and 4 this time. And then top and bottom. You're going to have to solve this thing for z, right? To get your... Now,
Would you use plus and minus?
I would probably go from 0 to the top and then double the answer. Because it's a volume problem, I would do that.
Set the origin.
Yeah. So it would be something like 0 to 2 pi, because I know I have to draw that whole thing. I know my radius goes from 2 to 4, right? My z restrictions are from 0 to the top of the sphere. 0 to the top of the sphere. The sphere is that solved for z, right? Which was square root of 36 minus x squared minus y squared, right? But I'm in, I keep on saying it, I'm in cylindrical, which is like polar. And so minus x squared minus y squared, that's the same as minus x squared plus y squared. That's really just r squared. So this top piece is just square root of 36 minus r squared, isn't it? Now I forgot, I have to double this because this is a volume, right? I'm integrating what? 1. Then r because I'm in cylindrical. Then dz, dr, d theta. I don't know if you followed that, but that's it right there. Oh, I did it a little different on the computer. I didn't double it. I went to 2 limits. But if you work it all out, I don't know if this works out, by the way. Just setting them up is what I'm looking at here. You get approximately 383.595 cubic units, whatever those are. Look at that, I knocked out 12.6. That's your homework, it's only 3 problems. Next class, spherical coordinates. After spherical coordinates, change of variables. Yep.